Hello class, in this video we're going to start with a little opener, a little refresher on the numerical, well, I won't call it the limit process that gave us the slope of a tangent line. So remember that was the limit as h approaches 0 of f of a plus h minus f of a divided by h. This is what we ended our last unit on. Pardon me. So what we're going to do here is we're going to take the equation of, we're going to take the slope of the tangent line, find the equation of the tangent line, and then find the equation of the normal line. So our function is f of x squared plus 1, so we got to write down our usual values. A is 3. F of a, so that'd be f of 3. 3 squared is 9 plus 1, that's 10. And let's look at f of 3 plus h. This equals 3 plus h squared plus 1. Now, this isn't quite as complicated as the one I gave you on the review, but let's go ahead. I'm going to kind of fast forward. This would be 9 plus 6h plus h squared plus 1, which gives us 10 plus 6h plus h squared. So we'll go ahead and plug that into our limit. Limit as h approaches 0 of 10 plus 6h plus h squared. So that's all f of a plus h, and minus f of a, which was our 10 up here. All over h. Okay, we can cancel some stuff out. And just to kind of save time, since we've seen this process before, I'm going to cancel the 10, and then very discreetly, I'm going to cancel all the h's at the same time. Not proper to do that. It's not proper decorum when you're in a calculus problem, but nobody has to know. So we end up with 6 plus h, and then we can plug in our 0, and we get 6. So this was the slope of our tangent line, also what we called the instantaneous rate of change. So when writing out our equation, we get y minus 10 equals 6 times x minus 3. We'll distribute, we'll get minus 18 plus 10 is minus 8, so that'd be y equals 6x minus 8. Okay. And now we're going to get the normal line. So the normal line is y minus 10 equals negative 1/6 times x minus 3. We distribute, we get positive 3 over 6, which would be 1/2, plus 10 is 10.5, which would be 21/2. So we end up with y equals negative 1/6 x plus 21 over 2. Now, some other names we'll go over. This was our instantaneous rate of change. It's the slope of our tangent line. It's also called the numerical derivative, and that's what I almost let slip earlier. That's what we're going to be talking about today, are derivatives. So our new topic, derivatives, some stuff to know. The derivative of a function is a function that helps determine the instantaneous rate of change at any point of a function. So if you consider and reflect on what we just went over, when we use the limit process that we've been using, we're only finding a single slope of a tangent line at a single point. What the derivative does is a function that helps us determine the instantaneous change at any point. So if I gave you 3 different points and said, find the instantaneous rate of change for the slope of the tangent line, or the slope of the tangent line, pardon me, at these 3 points, instead of doing 3 separate limit processes, we can now do this process right here once and then plug in our individual points because it's a function. There is an alternative definition, and it's right here, and we will go over both of them today. Some notation, dy dx, and then d subscript y x with a y, f apostrophe x, y apostrophe, and then d dx f of x. So these two right here, we say the derivative of y with respect to x. This is called f prime of x. That little apostrophe just means prime, y prime. And then this right here, the derivative of f of x with respect to x. They all mean the same thing. We're going to mostly use this one. We're going to use this one. And a little less often we'll see this one, and then even less often than that we'll see this one. This one we don't use very much in class, but textbooks like to throw it in there on occasion, and it is something that is commonly used in textbooks. So I like you to at least be aware of it. So when you're coming across your homework problems, if they decide to throw that notation on you, just be aware that all of these just mean the same thing. We say them differently, but they're all representative of what a derivative is. All right, some important facts. If a function is differentiable at x equals a, then it is continuous at x equals a. This is a true statement. And this will be important because when we talk about continuity in the past, we're also going to be talking about differentiability in the future. So being able to talk about both is important. So we will say that when it's differentiable, we know it's continuous. Now, if a function is continuous at x equals a, then it is differentiable at x equals a. This is actually false. We would like it to be true. And on the very next slide, we'll look at some examples of why it's false. Now, just to clarify, false in truth logic does not mean it is always not false. It just means it's false one time. Whereas true, it has to be true 100% of the time. And we'll look at some examples of why that is the case. And just a little geometry review. This first statement in number 1 was a conditional statement. Number 2 is its converse. Okay, converse and their original conditional do not always have to have the same truth value. So number 3, if a function is not differentiable, then it is not continuous. This is its inverse, and inverse and converse always have the same truth value. So this is also false. Okay. Then finally, if a function is not continuous, then it is not differentiable. This is actually true. This is called the contrapositive. It's actually kind of helpful because if we can look at continuity and see that it is not continuous at a point, then we know it's not differentiable. But if we see it's continuous at a point, then we need more information. So what's that information? So derivatives. At which points is a function not differentiable? And that probably deserves a question mark. So this first one is just a single solitary point. When discontinuities exist. If the point can't exist, then, or the limit can't exist, then we can't have any derivative to exist. So this is holes, vertical asymptotes, jumps, black holes, that kind of thing. So where else? Well, these 3 graphs are going to demonstrate when a function is continuous but not differentiable. And the things we look for are corners. This is a corner, so a corner is when a function is not differentiable, so not differentiable at x equals 3. And this would be a good representative. It's continuous. I like to refer to continuity as, can I trace along the graph without having to lift up my pen? And at that point, I certainly can, but it's not differentiable. And the reason why is we got to look at derivatives as tangent lines. The natural inclination is to assume, oh, I've got a tangent line right there. Remember, a tangent line intersects at only a single point. But because it's a corner, and the way it's specifically designed, we could also draw a tangent line there. We could also draw a tangent line there. So infinitely many tangent lines exist through that point. Same for here. This is what your homework will call a cusp, although I've often just referred to it as a corner. So not differentiable. Where's that cusp? That's at x equals 0. And same reasoning as this. We could draw infinitely many tangent lines. Now, the reason is because as the tangent line gets closer and closer, it slowly starts to get steeper and steeper, and until the real tangent line is actually an undefined line, which has an undefined slope, or a vertical line that has an undefined slope. And then finally, we have this one over here. Hold on. There we go. This will have a vertical tangent line, although realistically, we could look at this in the same light. We have many tangent lines that could theoretically go through that point. So this is just a vertical tangent line. So this is also not differentiable at x equals 0. Okay, so let's look at some examples. Given the graph lists all intervals of continuity and intervals of differentiability. So we can see we start at 0 and we end at 10. So we can see we start at 0 and we go to 10 uninterrupted. So our continuity is from 0 to 10. But we have these corners here that break up our differentiability. These are key points to look at when deciding if it's not differentiable. So differentiable, so we start at 0, okay? And the endpoints would not be differentiable either. That's probably a case I should include. But we're differentiable along this entire segment until we get to 5. So 0 to 5. And then we can close our first interval down. Then we go from 5 to 8. So that's another interval of differentiability. And then we go from 8 to 10. So while we have one continuous interval from 0 to 10, our differentiability gets broken up into 3 sections. So go ahead, try the next 4 examples on your own, and remember all the rules. All the rules. All these cusps and corners and vertical tangent lines, plus don't forget about your holes, your vertical asymptotes. If those don't exist, or those do exist, then differentiability does not exist. Okay, so let's, given the graph, list all the intervals of continuity and differentiability. So we're starting at -4. So when you're deciding differentiability from continuity, identify your corners and your cusps first. So here's one at -2. Here's another one, very slight, but it exists at -1. Then we got one here at 1. So we got 3 different corners of non-differentiability. So we should have 4 different intervals. So we're going from -4 to -2. I'll actually list these out vertically. And we're going from -2 to -1. And then -1 to +1. And then +1 to 3. And we're done. All right, here we go. We've got this graph. So a continuity. Now continuity is a little bit different on this. It seems like we've got a discontinuity here. So that would be at 1. So we're starting at, we'll say, we'll go with -infinity. And we go all the way uninterrupted to 1. We'll assume that goes on forever too. Then we go from 1 to infinity. So now corners and cusps, but also discontinuities. So we got to remember this one right here. So we have 2 instances of non-differentiability. So we should have 3 intervals. We start at -infinity. We go to -2, it looks like. And we go from -2 to 1. And we go to 1 to infinity. All right, here we've got, looks like a vertical asymptote at 1. We've got a corner here, and we got a jump here, or I should say a cusp. So we'll consider that an arrow. We'll consider that an arrow. So our continuity, but we've only got 2 discontinuities. So we've got 3 intervals of continuity. So we go from negative infinity. We have the vertical asymptote. It looks like it's at -1, so we'll go with -1. And then from -1 all the way to 2, right there. And then 2 to infinity. And then our differentiability, we have the two discontinuities, plus we also have this cusp here. So we're going to have 4 intervals. We go from negative infinity to -1, like we started continuity with. And then from -1 to 1. And then 1 to 2. And then 2 to infinity. All right, last one. Here we go. We got continuity. Where are our discontinuities? We got at 1, we've got at 2, we've got a vertical asymptote at 3, and we've got at 4. So we got 1, 2, 3, 4 discontinuities. So we're going to have 5 intervals of continuity. Well, there's an arrow. There's an arrow. So we're starting at negative infinity. Okay. We're going all the way to 1. And then we go from 1 to 2. And then as you can see with the vertical asymptote, we'll immediately go from 2 to 3. And then 3 all the way to 4. I'm just really testing to see if you can count out to 4. And then 4 to infinity. So there you go. 1, 2, 3, 4, 5. Do we have any other points? And the answer is no. So the differentiability in this case, I'm just going to write, it's going to be the same. Same as continuity. We don't have any additional corners or cusps or vertical tangent lines. We have just discontinuities. Great. All right, so let's go ahead and use the limit definition to find the derivative of x cubed. Okay, so I'm going to go ahead and do green on this one. We get the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so f of x is just x cubed. We don't have an a value, so we need to figure out what f of x plus h is. And as usual, without the numerical value, it's just x plus h cubed. Now, go ahead to take time to check my work on this, but I'm going to go ahead and say what this is right away. I won't include. Let me see if I can get my, there we go. So this is equal to x cubed plus 3x squared h plus 3x h squared plus h cubed. That's this part right here. I took a shortcut. Again, feel free to check my work on that, but that is correct. So we're going to go limit as h approaches 0 of this. So we have x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, all of that over h. And we can go ahead and do some simplifying here. We can see the x cubes will cancel, and then once we get that out of the way, we have an h that we can cancel out of each of these. So we'll be left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Oh yeah, forgot to cross this out. And then we can just plug in our 0. So when we plug in our 0, this will cancel, this will cancel. So our limit is just 3x squared. So the notation that was used was f prime of x is equal to 3x squared. And now if I were to give you a point, say find the slope of the tangent line at this point, you plug it in for x and you have your answer. So let's go ahead and use the definition of the derivative. Let's do one more with the square root of x. So again, I'll write it out. I'm going to use blue this time. Limit as h approaches 0 of f of x plus h minus f of x divided by h. So let's go ahead and get our f of x plus h. Well, that's just square root of x plus h. So nothing exciting going on there. There's nothing to distribute. So let's go ahead and write it into our limit. The limit as h approaches 0 of the square root of x plus h minus the square root of x divided by h. Now, this is where we're going to have to get into our bag of tricks. So our bag of tricks says when we have the radical like this, we multiply by its conjugate. That'd be square root of x plus h plus square root of x. And same on top and bottom. Square root of x plus h plus square root of x. Okay, and we create our difference of squares, so it's the limit as h approaches 0. We get x plus h minus x all over. And then as usual, don't distribute the h in. Don't do any distribution there. We'll just have to undo it later. And then we can do some canceling. And again, in the interest of space, I'll cancel that. And then in proper order, I'll cancel that, which just leaves us 1 at the top. So we got the limit as h approaches 0 of 1 up top, and then the square root of x plus h plus square root of x. Now, when we plug in h equals 0, we get square root of x plus square root of x right here. And then that's just something plus itself. Well, when we have something plus itself, we multiply by 2. So our final answer is 1 over 2 square root of x. And so f prime of x is equal to 1 over 2 square root of x. All right, number 4 says let's use the alternate definition of a derivative to find the slope of the tangent line at x equals 2. So the alternate definition was the limit as x approaches a of f of x minus f of a divided by x minus a. Okay? So we can start this like we always do. Identify a, it's 2. F of 2 is 1/2. But we actually don't need to go any further than that because we don't have any f of a plus h in this definition. So it ends up being the limit as x approaches 2 of f of x, that's just 1 over x, minus f of a, well, that's 1/2, and then x minus 2. Let's go ahead and get a common denominator. Let's go ahead and multiply this by 2, this by 2, this by x, this by x. The limit as x approaches 2 of, we get 2 minus x over 2x all over x minus 2. And that looks kind of clunky, but that's okay. Let's go ahead and multiply by 2x on top and bottom so that we can uncomplexify this fraction. Yeah, that's a real word. I made that up just now. And also at the same time, this 2 minus x can be reversed, and we have to account for a negative. So let's go ahead and do that. Oh, sorry, used to writing h. The limit as x approaches 2. So we got x minus 2, and I'll go ahead and put the negative out front. And we have 2x times x minus 2. As usual, we won't distribute, and then we can see, we can cancel that out. And then we get the limit as x approaches 2 of -1 remains up top over 2x. We can plug in 2, and we're going to get -1/4. So an alternate way of getting where you need to go. And that certainly is probably less messy than what we were dealing with a plus h. But, ultimately it's preference. This stuff has been around for thousands of years, maybe even just hundreds probably. But some stuff has been around for thousands of years, and mathematicians always find different ways, and you learn those different ways and get to the same conclusion and pick your preferred way. All right, last couple problems. Determine the numerical derivative to approximate f prime of 2, given that f of x equals 3. So we're going to kind of take an approach here that's called the numerical derivative. And it's really just an approximation. So the formula is f of a plus 0.001 minus f of a minus 0.001 all over. Think about there's a difference between a 0.01 both above and below, so it'd be 0.001 minus a negative 0.001. Now this will just end up being in the bottom will just be 0.002. And that'll be a constant. Now, I don't know what's special about the 0.001. Remember that in spirit, it's just let's get as close to the value as possible, but let's also keep it equal on either side. And the textbook we use picked 0.001. I don't know how common that is, but we're going to roll with it. So we're talking about cubing 2.001. Let's talk about our values. 2.001 cubed and 1.999 cubed. So 2.001 cubed, definitely not doing it on a calculator right now. I definitely had this prepared. We'll go to 3 decimal places, 8.012, and then 1.999 cubed is 7.988. So we'll subtract those two. 8.012 minus 7.988. We get 0.024, and then we'll divide by 0.002, and we get 12. Now, this was x cubed. Let's go back and check our previous problem when we got the derivative. Let's plug in 2 and see what we get. So it was right here. If we want to check that approximation, we get f prime of 2 is 3 times 2 squared. 2 squared is 4 times 3. Hey, look at that. It's 12. Go ahead and try this one now, and then we'll come back to it. All right, so let's remember our formula. F of A plus 0.001 minus F of A minus 0.001 divided by 0.002. So we're going to have 10.001 squared. So that is, hold on a second, I had it right here, 100.02. And then minus we're going to have 9.999 squared 99.98 divided by 0.002. So we have 100.02 minus 99.98, and then divide that by 0.002, and we get 20. Now we never did get a derivative of x squared yet. We'll learn that in the future, so we don't have a means of checking it. You could check it on your own, though. Last couple of slides, determining the derivative from graphs. Some things to look for. You got to remember that when we're figuring out a derivative, we're helping us find the slope of a tangent line. But since the derivative is a function, we can create ordered pairs and plot those on the graph. So when the original function is increasing, the derivative will be above the x-axis. That makes sense. Increasing would lead to positive slopes, would lead to positive points. So when the original function is decreasing, the derivative will be below the x-axis. When the original function hits a minimum or maximum, this means the slope of the tangent line is equal to 0. The derivative will intersect the x-axis. A function with a vertical asymptote and will have a vertical asymptote at that same point in the derivative. The converse is not necessarily true, and we'll see examples like that in the future. Keep an eye out for anywhere the derivative won't exist on the original graph. And an oscillating curve will have an oscillating derivative. We'll take a look at examples like that in the future. So exit ticket, rank these concepts for which you feel most comfortable, 1 to least comfortable, 4. If there are any additional details you want me to know, please give me to those as well.